Okay, here we go. Going to do a couple more examples. We got CCl4, carbon tetrachloride. Is it polar or nonpolar? Look at the shape. Look at where the electrons are. CCl4 is a nonpolar molecule. We've got the electronegativity numbers are all equally balanced out. Carbon a little lower in the middle. The chlorine's quite a bit higher around in every direction. So we got four dipoles that balance each other out. Electrons being pulled in all four directions away from the central carbon. We've got more than one axis of symmetry, multiple ways to fold this thing. So it's got a symmetrical shape and a symmetrical distribution of electrons. It's a nonpolar molecule, just like CH4, really, except that the dipoles are going in the opposite direction of CH4. Okay, we've got chlorophosphane. This is PH2Cl. PH2Cl, the name of this happens to be chlorophosphane. Is it polar or nonpolar? Look at the shape. Look at where the electrons are. This is going to be a polar molecule. Here is why. This one's a little tricky. But the electronegativity numbers are kind of lopsided. Hydrogen and phosphorus have the same electronegativity. Chlorine is quite a bit higher. Okay, so that means that we've got dipoles pulling electrons towards the chlorine in this molecule, away from the hydrogen, away from the phosphorus, away from the hydrogen, towards that chlorine with a higher electronegativity. So these dipoles do not balance out. We've got a lot of electrons over here as well. So we got a negative end to this molecule and kind of a positive end down here. And overall, we can only draw one axis of symmetry. There's only one way to fold it. That means it's got an asymmetrical shape, asymmetrical distribution of electrons. This is a polar molecule. Okay. C2H4. C2H4, or ethene. Is it polar or nonpolar? Look at the shape. Look at the bonds. Look at the distribution of electrons. This is a nonpolar molecule, C2H4. All right, the electronegativity numbers are equally balanced out. The carbons have a little bit higher electronegativity, and then the hydrogens in these four directions have a lower electronegativity. So we've got dipoles where the electrons are being pulled slightly towards the carbons in the middle. The dipoles balance each other out, and we've got more than one axis of symmetry. Multiple ways to fold this molecule, C2H4. So it's got a symmetrical shape and symmetrical distribution of electrons. Nonpolar molecule. Excuse me. All right. One last thing I want to remind you. You can have a nonpolar molecule that has polar bonds in it. This is a polar bond between the carbon and the chlorine. Carbon has a low electronegativity. Chlorine has a high electronegativity. So electrons are being pulled more strongly towards the chlorine. That's a polar bond. But overall, we've got four polar bonds just like that, balancing each other out. Polar bond down here balances out the one at the top. The polar bonds on either side balance each other out. So overall, this is a nonpolar molecule. It's got a symmetrical sharing of electrons all in all directions. So it's a nonpolar molecule, but it has polar bonds. This is a very important distinction. You can have a bond that's polar in a nonpolar molecule. Okay, that brings us just about to the end of polar or nonpolar. One last thing to remember. Why do we care if things are polar or nonpolar? It has a lot of important effects on things like melting point and boiling point and vapor pressure, whether the materials will dissolve or mix with each other. The polarity, whether something is nonpolar or polar, is incredibly important in chemistry, and we'll be seeing more about that coming up soon. Okay, thanks for watching.